All right, hey guys, I wanted to record a little help session for those of you that may be on flex. You may have missed class, or I will be out tomorrow, which is Thursday, October 17th, and some of you may need a little bit more guidance with this lab. For those of you that were in Wednesday classes, I kind of walked through most of this with you just to majorly hit home some of these points about convection. For this lab, you will need the gizmos pulled up, and it is called convection cells. It looks like this to begin with. So that's what it looks like to begin with, convection cells. Okay, it's in each one of your classes. Also, you will need the class kick, which looks like this. It's called Convection Cell Lab, due 10/17, should say 10/18. I'll change that today. Um, to begin with, the prior knowledge, all of this vocabulary is stuff that you know already. Convection cells, density, global conveyor belt. If you did what you were supposed to do, the notes that are due Wednesday, Thursday are Miss Tarpon discussing global conveyor belts in the oceans, and that's what that refers to. The mantle, mid-ocean ridge, subduction zone, vector. We're not going to talk about viscosity. I took that out of this lab just because it was a little bit redundant and outside of our standards. I didn't think we really needed it. So you won't see viscosity in what we're discussing today or on your lab, okay? Prior knowledge. Why do you think some of the soup, if you read the prior knowledge question there, there's a pot of soup in the stove, soup warms, you notice some areas rising where others are falling. And what do you think, why do you think that some of the soup is rising? If you can remember back to talking about the mantle, why is it rising? So why does it rise? Heat rises, cool falls, right? And so why counter to that, why do you think some of the soup is sinking down? Getting down towards the warm up, again, they're graded on a large scale, as in, did you do it or not? Because it's opinion based, and so there's not one answer. All of our answers may be a little different. So, when fluid, gases, liquids are heated, they tend to move, right? This motion is called convection. We talked about the law of conservation of energy, how energy is transferred from place to place in different forms, those forms being radiation, convection, conduction. And this is specifically on convection. So it's a large concept in earth science. Okay. And today, the reason we're doing this lab is because we get to make some major connections with convection and all the things that we have learned in the mantle and all the things that we are currently learning in the atmosphere and all the things that we're going to learn with oceans and weather. Okay. To begin, make sure you're in the model tab. There is a beaker of water, right, or liquid. Okay, so make sure you're at this screen. And it says click play. What do you notice? You can see those molecules moving about in there. And what do you notice? What do you notice with this? Again, this is a help kind of lecture. I'm not going to give you a bunch of answers to this. You'll have to make your own answers. But you can see the molecules in there in motion. Notice, where are they rising? What's happening at the top of that water? Where are they falling? Drag the eyedropper into the beaker just above the burner and let it go to release an orange liquid into the beaker. What do you notice about its path? So I'm going to drop this in here. Oops, I need to turn off micro. What do you notice about its path? Where is it rising? Is that in relation to the heat source? Let's move it, right? Let's move it. See. What about if we move it over here? Is it moving differently because we moved the heat source? What is the relationship there? We'll move it back. Okay, so that should give you some good walkthrough on the first page there. Again, this one is 10 points, but it's total, and your answers will vary. Activity A, before you begin this, make sure you click reset, turn burner A to high, and you're going to hypothesize. Okay, play, add a drop, watch the motion of liquid. Why do you think convection tends to occur in heated fluids? Why do you think convection tends to occur in heated fluids? I'm going to flip over here to actually the Nearpod for Friday and give you a visual what this question is asking. It's asking you to hypothesize. What do you think is going to happen to these molecules as we add heat? Are they moving faster, slower? Okay. Are they beginning to rise or fall as we add heat? If we go back, what happens as we add cold? Oh, they become really tightly packed, right? So the more these molecules are heated, the more energy they give off. As they give off that energy, they begin to rise, which is because they decrease in density. The opposite is true for if we add cold, okay? These molecules sink, and they sink. As they sink, they become more tightly packed, and that's density. So this will help lead us through some of the concepts here of why convection is the way it is. So they become tightly packed. They're denser. That's why they fall. So within the class kick, hopefully that helps you answer number 1. Observe number 2. Click clear drop, show temperature. And this one is what you need to pay attention to because these answers are graded. Show temperature. And you can tell that that is, you can see blue is cold, obviously, and red will be hot. We're going to click play here, and you can see the energy difference there. All right, moving A, B, C, and D. Where is the hottest liquid located? All I need from you here is bottom or top, okay? Just type bottom or top there for A. Where is it hottest? Bottom or top? Where is it coldest? Bottom or top? C is at a drop, okay? Does the hottest liquid tend to rise or sink? So for these two, for C and D, all I need is rise or sink. Does the hottest liquid tend to rise or sink? Again, thinking about density here. Click clear drop and add a new drop to the liquid. Clear drop, add a new one. Turn on show micro view. Oop, that's vectors. All right, and what do you notice? Where do they move the fastest? Where are those molecules moving the fastest? This has an answer too. Is it at the bottom or the top? Is it bottom or top? Where are they moving the fastest? And again, go back to that I showed you at the very beginning, right? What happened when I set the flame higher? B, don't let this one trick you. In which part are the liquid molecules the most spread out? Where do you see that circle go? Wah, out, right? Is it pretty relatively the same? We're looking at it there. As it moves away, it's relatively the same, It's going down, same. And then as it moves back towards the heat source, it goes way out, okay? So please pay attention to that. Is it at the bottom or is it at the top where they are most spread out? Number 4, click clear drop and add the probe. Very important process here. Add the probe, and we're going to look at the relationship between temperature and density. So the probe's down here at the bottom. You can see temperature is taking on down further. See 92 degrees Celsius. Check out the density over here. It says 0.83 grams per milliliter. As we move away from the heat source, as we go down in temperature, I want you to watch what happens to density. So as we're going away from the heat source, look at that number. What is it doing? Is it increasing or decreasing? And we'll stop here at 23 degrees Celsius, 0.98 grams per milliliter. Well, we started at 0.82. So what is that relationship like? Is it as temperature goes up, density goes up? Or is it as temperature goes up, density goes down? Or could you say it like it is inversely related? As one goes up, the other goes down. That's what that means. So take a peek at that, see what you can get. I want to see what those answers, I'm curious to see what those answers are. Again, you just take your probe, move that around. We start at 85 degrees Celsius there, 0.85 grams per milliliter. And then what happens to that number as temperature goes down? What happens to that density? Why do you think that this relationship is so? And then in number 5, and this is just taking what you're learning in number 4 about the relationship between density and temperature and adding it to like a real world scenario. So like if we drop a rock in water, why does it sink versus something that's sitting on the surface and floating? How does it relate to how we just observed the liquid in that beaker? Moving on to page 3. And this is the real important part here, guys. This is the connection. This is taking what we just learned about convection specifically, and we're adding it to real world convection. Where do we see this? Well, we see it in the mantle. We see it in the mantle. We see it in the atmosphere, in the ocean. We see it at the coast as well. And so this is highly important, highly connective to everything that we have done and everything that we are doing. So the first thing we're going to do is we're going to make sure mantle is selected. We're going to click play. Again, I'm not going to give answers here, but I am going to walk you through how to do it. And we know that the core is our heat source within interior Earth. Okay, so it makes sense then that material is going to be hotter down towards the core. Okay, so what is the general pattern of the magma? That's your first question. What's the general pattern, right? Heating, rising, cooling, falling, heating, rising, cooling, falling. And you can see that as it rises at the mid-ocean ridge, it cools and spreads out and falls at those subduction zones. So take some time, click on these. All of this vocabulary should be familiar. Number 2 says, click the central orange dot, the mid-ocean ridge, read about it, okay? What's happening along that mid-ocean ridge, right? What I just said, heating, rising, cooling, falling. What part of that is occurring at the mid-ocean ridge? And then what part of that is also occurring at the subduction zone? What's happening here as it's rising at the mid-ocean ridge and falling at the subduction zones? Japan sits on a subduction zone. That's where question number 3 comes from. And what natural disaster did we talk about happens at those subduction zones? You could pick 1 or 2, really, for that. But subduction zones, what natural disaster happens? What do you think would be common in Japan? Now, again, Ms. Tarpon did the lecture on oceans. So we're going to switch gears here. We're going to go to oceans. Talking about this conveyor belt. And we got 2 places here. You can see the red for the warmth, and you can see the dark blue or blue for colder water. All right. So what 2 reasons causes water to move downward? Well, convection. What causes that water to move downward? There are 2 reasons, salinity being one of them, which causes that water to be denser, but also because look at where it is. Look at where it is up here in the north, right? North Atlantic, very cold, very salty water. And that warmer water, when it comes to this area, it begins to sink because of 2 reasons. Because as you can see here, because it's colder, because it's saltier, that makes it denser. And so it sinks to deep, deep ocean. And as it hits that conveyor belt, it's going to move throughout. But what is it encountering when it comes down into here? What is this line? It's technically not a line, but it's a line. We're going to give it a line that goes across the middle of the Earth. What do we call that? Hopefully you're settling on equator. And what do we know about the equator? It's very hot. So what happens there? What causes the water to rise? Well, heat does what? We know a lot about convection at this point. Cold sinks, heat rises because of density. So in these places, right, it contacts this warmer water. It begins to come up. We have this upwelling here. That's what we call it. We have downwelling in the North Atlantic. And we have upwelling over here off the coast of Africa there. Question number 4, infer why upwelling zones might have more fish. Well, think about it. If you think about any organism, where are you going to find a denser population of any organism? Where, what brings those organisms to these locations? Well, food, right? Food. So at these places where it's that water's coming across the bottom of the ocean, it's bringing up all of those nutrients, very nutrient rich water off the coast. And so these upwellings create a lot of nutrient dense places for fish. Moving on to page 4 is the coast. We're going to switch gears, go to the coast here. Start with day. You learned in the solar radiation lecture, right, that land is darker, just like wearing a black shirt versus a white shirt out in the sun. That darker land is going to absorb more solar radiation while the sun is out. Okay, so that land absorbs that solar radiation. It's going to be hotter than the oceans because, again, the ocean reflects, that water reflects. It's still absorbing some, but it reflects more than it's absorbing during the day, right? And so above the land, it makes sense, heat rises. That's convection. So above the land, heat rises, and of course, it's going to fall back down over the ocean. If you're standing on the beach here, you would experience a sea breeze, a breeze that is coming in off of the ocean, a sea breeze. Okay. The opposite is true for night. So whereas water holds heat energy longer, it takes longer to absorb. Just like if you were in summertime or early summertime, you know that you don't go swimming until what, that May, June. You're risking it if you go swimming before that. I don't even get in the water till July because it's too cold for me. But it takes longer for that water to heat up, but it holds it better. Okay. And so at night, what we have is the ocean that has held some of that radiation. Okay. And then that evaporation of this water is coming up, creating clouds. All right. And then across the land, it's sinking back down. And you get this land breeze. Okay. So from the land going out. The question on number 3 states about a sailboat, right? If you were going to sail, would you rather sail during the day where you're fighting against this breeze? Or would you rather sail at night where the breeze is helping you? Moving on to atmosphere, what we're really studying. Okay. Observe, select atmosphere, large scale convection cells. Okay. So we're going to click play. And we see that we have warmer air around the equator. That makes sense, right? It makes sense. The equator's hot. So that warmer air around the equator rises. Again, convection. And why does it fall? Why does it fall? Well, it falls as it moves away from the equator. It encounters less heat, okay, as it moves away towards that 30 degrees north line, right? And it starts to fall. That cooler air starts to sink. All right, we don't really have to get into Hadley cells and Farrow cells and polar cells, but rises at the equator, falls at that 30 north and south, both sides of that line. Okay. Let's see, go back. The question at the very end, C, because we're not doing number 7. We're really going to learn on Friday of this week if you watch this before then. But talking about weather, I really want you guys to understand this concept. If you're like, look at my video. As that warm air rises, as those molecules rise, they vacate the surface. The surface becomes vacant, right? There are less molecules down here, right? So if you're thinking about pressure, well, if there's less molecules because of the rise of those, the ones that were there, we get low pressure. There's not a lot of pressure down here because of the rise. And if we go back to over here, you can see that here, okay? Cloud formation. So as it rises underneath, it creates low pressure. It vacates, creates low pressure. And bad weather is generally, or rain, precipitation is generally associated with those low pressure systems. Think hurricanes, okay? Also, the opposite is true for cold, okay? So that cold weather, as the cold weather sits on the surface like a blanket, it becomes more dense. You know, it drops and it gets more dense, and those molecules become tightly packed. That creates high pressure. Well, it puts pressure on the surface. That makes sense, right? So it's not like a blanket. So that high pressure system is generally associated with good weather. Okay. So C says why our climate's generally wet near the equator and generally dry around the latitudes 30 degrees north, 30 degrees south. Use what I just told you to answer that question. All right. Don't do number 7. That relates to activity B. I think do not do number 7. I have that down there for you. And then make sure that you guys get this completed. This is not an OHS assignment. This is a class kick assignment. So I will be grading these within class kick. So you do not need to submit anything. All right, guys. Hope this helps. I will see you soon.